All right, let's talk about one of the biggest, baddest unsolved problems in all of mathematics, the Riemann hypothesis. For over 160 years, it has stumped the smartest people on the planet. But a brand new approach is giving us a powerful and, honestly, a surprisingly beautiful new way to attack it. So let's dive in. So what if I told you that this colossal problem, a problem that touches the very fabric of how prime numbers work, could be solved not by getting lost in the weeds of complex numbers, but by answering a much, much simpler question? Because believe it or not, that's the core idea here. It's a total reframing of the problem that boils it all down to a simple positivity test. If every single number in a very special, infinite sequence is positive, then boom, the hypothesis is true. But if even one of them turns out to be negative, the whole thing is false. So what is the Riemann hypothesis, really? Well, at its core, it makes a prediction about a tool called the Riemann zeta function. The easiest way to think about it is like a landscape, with hills and valleys. The hypothesis is all about the zeros, the points that are at sea level. It predicts that all the interesting zeros lie on one single, perfect straight line. Proving this would unlock some of the deepest secrets about prime numbers. But trying to map out every single one of those zeros is, well, it's basically impossible. So a different strategy started to take shape. What if we could test the hypothesis without ever having to look at that complicated landscape? And that's where this brilliant idea of a simple positivity test comes in. Back in 1997, a mathematician named Jianjin Li found something incredible. He proved that the Riemann hypothesis is completely equivalent to a totally different statement, which we now call Li's criterion. And what this does is it completely transforms the problem. It shifts it away from the location of zeros in that complex landscape to the properties of a simple, infinite list of numbers. And Li's criterion boils everything down to this one question. It's kind of like an infinite chain of dominoes. For the hypothesis to be true, every single domino from the very first one all the way out to infinity has to be positive or zero. If just one of them falls into the negative, the whole theory just comes crashing down. And this is the absolute key. There is a perfect one-to-one relationship here. Proving that all these Lie coefficients are non-negative isn't just like proving the Riemann hypothesis. It is mathematically the exact same thing. They're just two sides of the very same coin. Now, you might be thinking, okay, if the test is so simple, why hasn't anybody solved it yet? And that's a fair question. The reason is that actually calculating these Lie coefficients has been, up until now, an almost impossible task. This quote from the mathematician Andrei Voros really sums it up perfectly. For decades, this sequence of numbers has been like a ghost. We know it exists, we know what it means for the hypothesis, but trying to actually grab hold of it and calculate its terms has just been incredibly difficult. And here's the real root of the problem. The traditional formulas that were used to calculate the Lie coefficients were built from parts that flicker back and forth between positive and negative, completely unpredictably. Imagine trying to build a stable tower using bricks that are randomly switching from being super heavy to being super light. The whole structure is just unstable and it's prone to massive errors. But this is where a recent breakthrough by a team of mathematicians, McFidrin, Scott, and Mignon, just changes the entire game. They found a way to reframe the whole calculation, completely sidestepping that old problem of instability. This slide shows their breakthrough perfectly. Instead of using those unstable, sign-fluctuating components, their new approach builds the calculation from a different set of numbers. Numbers that are all provably positive. No more flickering. This really is the aha moment. By building the formula on a foundation of purely positive, stable numbers, the entire calculation becomes robust. You're not building with flickering bricks anymore. You're building with solid gold. But this new, stable foundation introduced one last challenge. It produced a really complex mathematical equation that needed to be solved to make the whole method work. It's like they built this beautiful, secure vault, but now they needed a special key to open it. Now, you do not need to understand every symbol here. Just appreciate that this is the mathematical lock they had to pick. It connects different parts of the problem in a really specific and tricky way, and your standard tools just aren't going to cut it. And here is the key. It turns out there is a special mathematical tool called the generalized Lambert function that is the perfect instrument for this job. It's practically designed to provide an exact solution to precisely this kind of equation. It opens the lock perfectly. So, with a stable foundation and the exact key to unlock it, what could this new method actually achieve? Well, the results are pretty incredible. Using this new technique, researchers were able to calculate the first 4,000 Lie coefficients. That's a huge leap forward in our ability to actually inspect this mysterious sequence. And they didn't just calculate them roughly, they did it with an astonishing 200 digits of accuracy, giving us this incredibly high-resolution view of these crucial numbers. And maybe the most stunning part of it all, this massive computational feat was achieved on a standard laptop. That shows you how powerful and efficient this new method truly is. It makes a once elusive calculation accessible to so many more people. So why does all this matter? Because now we know exactly what to look for. Theory predicts that if the hypothesis is true, these coefficients will grow smoothly and predictably. But if it's false, they should eventually start to oscillate wildly. We finally have a tool that's sharp enough to spot the difference. So far, all 4,000 coefficients they've calculated are positive, and they're behaving just as they should if the hypothesis is true. But this new method gives us a telescope to look deeper into this infinite sequence than ever before. The ultimate question remains, as we calculate the 5,000th, the 10,000th, or even the millionth coefficient, will that smooth pattern continue, or will we finally see a flicker and watch that first domino fall